Hello everyone, welcome to my introductory class, physics. We're going to be taking you through some certain topics, fundamental topics that you're supposed to know in physics. And in this class, we're going to be looking at the definition of physics. We'll look at measurement as a major topic. But we're going to just introduce you about to the definition of physics. So what is physics? Physics is a pure natural science that studies matter, energy, and fundamental interactions between them, alright, in space and time. So physics is a pure science that studies matter, energy, fundamental interactions between them in space and time. So physics branches include mechanics. We can talk about mechanics, talk about electromagnetism, electricity, wave, whether light waves, sound waves, or other types of wave. Then, and some other aspects, and look at quantum, look at relativity, and all of that. Modern physics, quantum physics, just mention that. So, basically, that is what physics deals with. Physics studies matter, energy, and interactions between them in space and time. So basically, or majorly in this class, we're going to be looking at measurements. So before we look at measurement, a very key important thing to consider or to look into is what we call quantity. Quantity. What is quantity? Quantity is the property of a body or substance that can be measured. You know, we can talk about maybe a table, for example. We talk about length of a table. That's a property of that table. The speed of a particular car, right? So quantity is the property of a body or a substance that can be measured, right? Right. So then, for every quantity that is being measured, there is a yardstick through which the quantity must be represented. Okay, and that is called unit. Unit. So unit is the yardstick. Is the yardstick through which quantity measured, or through which quantity is measured. Let me put it that way. Through which the quantity is measured. Right? Having talked about quantity and unit, then it is now proper for us to look at types of quantity. Now, before we look at that, I did mention example. Example of unit could include centimeter or meter, seconds in terms of time, grams or kilograms in terms of mass, unit of mass, and so on. So types of quantity. We have two types of quantity. We have one, fundamental quantity, fundamental quantity. Then two, we have derived quantity. Right? So that's an error there. So we have fundamental quantities and derived quantities. What are fundamental quantities? Fundamental quantities. Fundamental quantities are quantities that are There are quantities that are independent of other quantities. Quantities that are independent. They are quantities that are independent of other quantities that are independent of other quantities. So, and what that means is that they cannot be defined. They cannot be defined or derived. Cannot be defined in terms of other quantities. Okay, so that means they are independent. They are basic quantities. So you cannot define them in terms of other quantities. You cannot derive them from other quantities. Like the illustration I always use for my students. You look at alphabets A, B, C, D. You can't derive A, you can't derive B, you can't derive C, you can't derive all the alphabets, all the letters in the alphabet. They are fundamental, they are basic. What you can only derive from those letters is 2-letter words, 3-letter words, okay, and so on. So they are basic quantities that are independent, that cannot be defined in terms of other quantities. So I'll give you the examples now. So you have fundamental quantities. We have fundamental quantities. Then we have the units, fundamental units. So fundamental units will definitely be the units of, they are actually the units of fundamental quantities. That means other units depends on them. They are also independent of other units. Okay. So the first one I want us to look at is mass. Mass is a fundamental quantity. It's usually represented with capital M. The unit is, the standard unit for mass is kilogram. It's kilogram. Alright. So kilogram, which is kilogram. Before I continue, let me also mention that it does not mean that there are no other units for mass, likewise other quantities, but the system internationally unit, which is called SI unit, I think the standard unit accepted is kilogram for mass. So even though we have more than one yardstick through which a quantity can be measured or represented, but yet there is a standard unit that is generally accepted, and that is called SI unit, System International Unit. So, and that is a fundamental unit that we're going to be writing for fundamental quantities. So the next one is length. Length. You can represent length with L, and the unit is, the standard unit is meter, which is M. We also have time. We represent it with capital T. Also, the SI unit is second. So below, we also have some other units like for time to be minutes, hour, but the standard unit is second. I also have electric currents. Electric currents. We represent electric current with I. So the unit for electric current is ampere. Ampere. Then 5. There's also temperature. Temperature, which is normally represented with theta. The unit for temperature is either degrees Celsius, or Kelvin. Then I also have luminous intensity. Before I mention luminous intensity, we have amount of substance. The unit for amount of substance is moles. It's mole. The short form is mole. Okay. Then we have luminous intensity. The unit for luminous intensity is candela. which is C. Right, so these are fundamental quantities and their units. So you have mass, program length, meter, and so on. So they are 7, usually 7. So the next thing to look at is, and these are their symbols. So the next thing to look at is derived quantities. Derived quantities, right? So what are derived quantities? Derived quantities. Derived quantities are quantities that are what? That depend on other quantities. So since we said fundamental quantities are independent, then derived quantities, just like the name implies, are quantities. So they are defined in terms of fundamental quantities. So basically they include area, volume, speed, and so on. So just like we mentioned under fundamental quantities that concerning fundamental units, there are also units that are independent of other units. So we have derived quantities. Then there's also, before I talk about their derived units, let me also include derivation or simply formula. So then we have units, right? So the first one we want to look at is area. Area is simply length. Area is length times length. So we are making use of length of a square. So it's length times length. The unit of length we have said before, that is meter. So it means you're going to have meter multiplied by meter, and the unit will be meter squared. Then also volume. That's length times length times length. So that will also be meter cube. Then you can also mention speed. Speed is distance over time. So distance, length, displacement, height, they all have the same unit, which is meter. So, and the unit of time before we said it is second. So the unit of speed would therefore be meter per second. You can also write it like this, raised to the power minus 1. Then we also have velocity, which is displacement divided by time. So I mentioned before that it's going to be in meters, so which is also meter per second, but you write it like this. So in continuation, so we have acceleration. So we have acceleration. So acceleration simply means change in velocity. Change in velocity. Change in velocity divided by time. So that's the derivation, that's the formula. So we have final velocity minus initial velocity divided by time. You can also express it as v minus u divided by t. That is final velocity minus initial velocity divided by time. So the change in velocity will only take meter per second. So meter per second per another second simply implies meter per second square. Or you write it like this, meter per second square. Alright, so that's the derived quantities. Okay, let me add more. We can talk about force also. Force is simply mass multiplied by acceleration. So mass is in kilogram acceleration is in meter per second square. But we don't normally use this because although if the question asks you to represent force in terms of basic units, you will make use of this. So, but what this implies is Newton. Okay, so the unit you normally use is the unit that is used is Newton. Right? So what else? Let's see if we can add more. We add more. Okay, and we had more. Okay, let me stop there. We can always do more derived quantities. Now the next thing, what I mentioned here will lead me to another thing I want to, maybe by doing that we can talk about some other quantities also. Okay, so and that is the units, deriving the basic units. So deriving basic units of derived quantities. So for example, if I look at pressure, pressure is force divided by area. Okay, that's the formula. If I want to look at the basic unit, okay, the basic unit, to get the basic unit of force, of pressure, I will first of all write the basic the formula of each quantity is equal mass times acceleration divided by length times length. Alright, so that will enable me to simplify this further. Now mass, we have said the unit is kilogram, multiplied by acceleration, the unit is meter per second square, and then divided by meter multiplied by meter, so which is meter square anyway. So we have kilogram multiplied by meter per second square. Then once this division change to multiplication, this meter square will become 1 over meter square, because meter multiplied by meter is meter square. So here we can have 1 meter cancel meter here, so that we have kilogram divided by meter second square, so which implies kilogram per meter per second square. But I would rather write it in terms of this is per second square, or per meter per second square. So if you are asked to represent a quantity in terms of its basic units or fundamental units, that is how to do it. You start with the formula, you simplify the formula, then whatever needs to be reduced, whatever needs to cancel out, you cancel it out, and then whatever remain will be the basic unit. You know that the basically or normally the unit of pressure is Pascal, or is either Pascal or you talk about Newton per meter square, because force is Newton, the unit of force is Newton, while the unit of area is meter square, so Newton per meter square Pascal. So that's that on that. So then with that I come up to, so basically you have that. Next thing to look at is dimension. What is dimension? Dimension is a process of representing quantities in terms of fundamental or in terms of basic quantities, representing derived quantities in terms of basic quantities. Okay, so for example, let's say I want to find the dimension of acceleration. Now there are rules when it comes to representing quantities in terms of in terms of basic quantities. So you should always make use of square brackets to when you're writing out your formula. For example, this would be acceleration is change in velocity divided by time. Okay, so you put it in square brackets. Okay, so change the velocity. Change the velocity, that is, we can simply say change the velocity over time. So meanwhile, the change in velocity is since velocity is meter per second square in terms of the unit. So what that means is it can be represented as length per t square, all right, divided by time. Time is t. So, right, so which means I can have L over t square. Oh, sorry. So I have over t. So that's supposed to be so multiply by 1 over t, because the division, when you change to multiplication, you invert the time. So this is simply L per t squared, because t multiplied by t will be t squared. So this is the dimension of acceleration. Okay, so still on dimension, let's look at our dimension of force. Force, we know that force is mass multiplied by acceleration. Okay, so don't forget, it must be in square bracket. So mass times acceleration. So we have mass is already a fundamental quantity. So, but that of acceleration will have to be change in velocity multiplied by time. So then to simplify it further, we have mass multiplied by change in velocity will also becomes displacement over time, all of them divided by time, right? So with this, we can now represent them with their first letter in capital letter. So we have this to be capital M multiplied by, this is capital L divided by capital T, also divided by capital T. So we have M multiplied by capital L over T multiplied by 1 over T. So finally our dimension is now M L R T squared. Okay, so that is that. You can also write it as or M L R T squared like this, raised to power minus 2. So right, so that is the dimension for force. Okay, which other one? Let's look at work. Work is equals to, formula for work is force multiplied by distance or displacement. Distance covered in the direction of the force. So since we already know the dimension of force, but suppose you were you did solve that of force earlier, you will follow the same process. So, but since I've already done it, so I'll just pick it up from here. The dimension of force is already, don't forget to put it in square brackets. So M L over T square multiplied by L. Don't forget I said you represent distance, displacement, length, height, you represent those things with L. So this simply means M L square, because this L multiplied by L, that's S square per T square, right? Or the dimension can also be, can also write it as this M square per T raised to power minus 2. Okay, so that is that on dimension. So as personal exercise, you can also go ahead and determine the dimension of the following. I'll just give you the derivation, the quantities and the derivation. For example, you have You have impulse. Impulse is given by force multiplied by time. That's 1. Then 2. Talk of momentum. Momentum is mass multiplied by velocity. Then let me also give you power. Power is work divided by time. So exercise. So you can go ahead and also derive the dimension of those 3 and some other quantities you can think of. Okay, so now I move to measurements. Measurements. When you talk about measurements, measurement refers to assigning values to physical quantities. It means determining the value of a physical quantity. Just like what I mentioned earlier, if you have to determine the particular property of a table in terms of length, the art of determining that length is called measurement. And measurement is very important in physics because virtually everything in physics has to be measured. And so it is very, very important. And we must also understand that measurement is not always accurate. Why is measurement not accurate? Because the instrument you want to use to measure may not give you an exact value. Okay, so it may not give you an exact value. So definitely you cannot have an accurate determining the value of the, or assigning the value of the property of a body as measurement. Okay, or determine the value of physical quantity. Okay, or determining the value of a physical quantity. Right? That's called measurement. So, and that is why, because we cannot determine the measurement of a physical quantity accurately due to the instruments that may not give us the exact value. That's why we have different instruments with their accuracy. Okay? So accuracy simply means the highest number of decimal places an instrument can measure in terms of the specified units of measurement. All right. So when you look at length, let's say measurement of length, for example, measurement of length. So the following instruments are used to measure length. Talk about 1, meter rule. Meter rule can have ruler also. Have calipers. Have vernier calipers. Then micrometer screw gauge. Micrometer screw gauge. So all these are used to measure length. So look at meter rule. Meter rule can simply measure the length of an object like table, length of a chair, length of virtually small objects around us. So the accuracy is always between 1 millimeter or 0.1 centimeter. So because the reason why it is 0.1 centimeter, if you look at your meter rule, it's always graduated from 0 to, the calibration is always from 0 to 100 centimeter. So, and that means that, which is, if you convert this 100 centimeter to meter, that's simply 1 meter. And that's why it is called meter rule. Alright. So the smallest unit, the highest number of decimal places meter we can measure is this, either 1 meter or 0.1 centimeter. The same thing is applicable to ruler. Ruler is more or less like meter rule. It's just that you use your ruler on paper. For example, the highest, the longest ruler you can have ranges from 0 to 30 centimeter or thereabouts. Yeah. So likewise, calipers is also used, especially by engineers, to do measurement of probably diameter of a circular object on the field. Then vernier calipers are micrometer screw gauge. For vernier calipers, we also have its own accuracy it has a better accuracy compared to meter rule, and that's why it can measure smaller objects. So its own accuracy is 0.1 millimeter or 0.01 centimeter. Then the accuracy of micrometer screw gauge can also measure very small objects, so it has better accuracy than vernier calipers. So you can talk about its own accuracy as 0.01 millimeter or 0.001 centimeter. All right. So the vernier calipers are used to measure objects such as internal and external diameter of a tube. It can measure diameter of a hole. Okay. Micrometer screw gauge are used to measure internal and external diameter of a thin wire. Right. So you can look at thin wire compared to tube. That's a very smaller object. So micrometer screw gauge can measure very small objects. Now the next thing to look at is how do you determine the measurement of vernier calipers and micrometer screw gauge? Let's say you are given this as your vernier calipers and you have this. Right. Now, this looks like a typical vernier calipers. So I will have if I have this, okay, so we have the vernier calipers given as this. Then definitely if we have, let's say this is 2 centimeter, let's say this is 3 centimeter, let's say this is 4 centimeter. So what that means is that each of these tiny units, each of these tiny points, and let's say I have my vernier scale to be this. Okay. Let me find 1, 2. All right. Now, don't mind me. Since I can make this one so clearly, let me correct something there. Okay. So, let me do this. I need to redo this. And so on. So perhaps I have this. Okay, though it's not that straight. Now this scale here is the main scale, while this one is called vernier scale. So the idea is you add the main scale plus the vernier scale for you to get the readings of these vernier calipers. This is the vernier caliper. This is how the output of the reading always look like. So you have the main scale and then the vernier scale. This is the vernier scale. This is the main scale. This is the vernier scale. So the main scale How do you read it? You come to the number that you have, whatever be the value before this main vernier scale starts its own reading. That is what you are going to store for main scale. This is 2 centimeter, which means that between 2 centimeter and 3 centimeter we have 0.1. We have a counting in 0.1 differences. So you have 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.93. So and if you look at where the main scale, vernier scale start from, that was after 2.3. So your main scale will be 2.30 centimeter. While your vernier scale, how do you determine your vernier scale? Your vernier scale is where the calibration on the vernier scale, where it aligns with the calibration of main scale. That is what will be your reading for vernier scale. So if suppose your vernier scale says maybe this one is 5, and then probably this one is maybe this one is 6, and this one is no, let's say this is 5 and this is 10, or let's say they did not even put anything there. Let's say nothing is put there, just written like that. So if nothing is put there, then it means this is your 0.1. You count it in two decimal places. So this will be 0.1, 0.2, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06 is where the calibration aligns with that of main scale. So if you look at it, it aligns, even though it was not that drawn straight. So this will now be 0.06 centimeter. So you add it together. So this will be 2.36 centimeter. So that is the reading of these vernier calipers. Then very quickly, if you have, you can also talk about micrometer. So suppose we also have vernier micrometer scale gauge like this. Okay, so and then you have so then you have this. So let's say this is 5. Okay. So let's say you have your micrometer scale gauge like that. So let's say this is 20, 25, 30, then there's any other 1, 2, 3, 4, 35. So micrometer scale gauge will always be in millimeter. Okay, so if you want to determine the reading, we also have main scale and you also have vernier scale. So for the main scale here will be 6 because you have an additional short line here. So this will be 6.00, while your vernier scale will be where it aligns with, where this horizontal line aligns with the reading on the vernier scale. So you have 25, 26, 27, 28, 29. So if you look at it, it's in between 28 and 29. So but then you use because I drew it slightly, it's supposed to be 29. So the idea is to make it 29. So that's going to be 0.29. Okay, so you add it together, and this will be 6.29 millimeter. So that is how to determine the readings both on the vernier scale and micrometer scale gauge. Right? Alright, so we also have measurement of some other measurements. Measurement of mass and weight. What is mass? Mass is the quantity of matter contained in a body. Alright, So mass is quantity of matter contained in the body, while weight is the Earth's gravitational attraction. The Earth's gravitational attraction on an object towards the center of the Earth. So if you want to measure mass, mass is measured by spring balance and is measured by beam balance, while weight is measured by spring balance. So we say mass is, we want to differentiate between the two. Quantity of matter, this one is quantity of matter in a body. Quantity of matter in a body, alright, while weight is Earth gravitational attraction. Gravitational attraction of an object towards the center of the Earth. Towards the center of the Earth. Alright? Towards the center, since we measured Earth here already. Then we said mass is measured using beam balance. Beam balance is usually used by those that cells measured with. Sorry, I have to be fast because I don't want this video to exceed the time frame. So measure with beam balance, usually used by those that cells. We are conversant with those that sells nails, and some other building materials. You will discover that you always make use of beam balance. So while weight is measured with spring balance. Okay, so spring balance. Another difference: beam balance operates on principle of moment. You'll be taught principle of moment in higher class. Spring balance operates with Hooke's law, which you are going to do later on in your higher classes. So you also have some other difference. Okay, so we also have some other differences. So let me call it 3. Okay, sorry. Let me call it 3. So mass is, of course, measured in, when we say measured in, we are talking about the unit, measured in kilogram, while this one is measured in Newton. Okay. Then mass is constant. Mass is always constant everywhere. Mass is constant. So no matter where you are, mass is constant everywhere. While weight varies. Weight varies from place to place. From place to place. Alright? So some other quantities that can be measured includes liquid. Liquid is measured with measuring cylinder, pipettes, burettes. We do more of that in chemistry. Then there's also regular objects and irregular objects. Some irregular objects are measured using what we call Eureka can. Eureka can is a can that looks like something like this. So that once that irregular shape is dropped into this water, then the spillover of the water will be to a cylinder that can be used to measure the volume of the irregular object. So, but for regular shape, you can simply measure the volume of the shape, whether length and breadth and height or any other. So the other one is measurement of time. What is time? Time is that which shows intervals between two events, right? So it's distinguished between two events. So when you talk about measurement of time, you can refer to make use of instruments such as stopwatch, stop clock, you have stop clock, you have wristwatch, you have a sand clock. This is a sand clock. Okay, Pendulum is also an instrument. Pendulum, the pendulum clock. So you have them like that. Then let me also mention that for volume, in order to calculate the volume of whether regular or irregular objects, you need to know your formula for. Sometimes you need the formula of density. Density is equals to mass over volume, and in fact you should add it to dimension that you're supposed to dimension, the exercise of dimension that I gave earlier. So you can also find the dimension of this. So most times, if it has to do with volume of circular object, maybe that of cylinder, you will need the formula for volume of a cylinder. Excuse me. You need the volume of a cylinder. Then you also need to have knowledge of diameter, circumference of a circle, area of a circle, in case you need to make use of area. Volume is the same thing as saying length multiplied by area. So some questions might require you to have to combine area of a circle with length. So something in that area. So you need to have the knowledge of that. So so far so good. We have looked at measurements, and we have looked at measurement of length, and then we looked at measurement of mass and weight. So I mentioned that you use beam balance to measure mass and use beam balance to measure weight. Then measurement of regular objects. If it is regular objects, you can only determine their length, measure their length, their breadth, and height to calculate the volume. So for volume of irregular objects, you make use of Eureka can. This is for irregular objects. Then or irregular solids rather. But if it is liquid, you make use of what is called measuring cylinder and pipettes, burette. You do more of that in chemistry. So all these talks about measurement of time, mentioned stopwatch, stop clock, sand clock, pendulum, wall clock, and so on. Wristwatch is also part of it. So these are, and I've also show you how to determine reading of vernier calipers, micrometer screw gauge. Okay. I was also talking about examples of what you use vernier calipers to measure, such as diameter, internal and external diameter of a tube. You can also use to measure thickness of a meter rule, okay, diameter of a hole, so on. Micrometer screw gauge, internal and external diameter of a wire. Just small, very tiny objects. That's what micrometer screw gauge can measure. So, like thickness of a paper. Okay. So, those are examples of what you can use those instruments to measure. Then let me also mention that it is always better when you are doing measurement that you put the you consider the error that might occur as a result of the instrument that is being used. So usually if your reading is something like, let's say 5.12, it's always advisable to put plus or minus 0.1. So plus or minus 0.1, so that we can know that it's either the reading is less than, that means it can either be 5.22 or 5.02. So because of error that can happen, instrumental error. Okay, for example, you have error due to parallax. So that's part of the error that can happen, because when you are not viewing your instrument or meter rule, when you are not viewing it within a straight path of the eye, maybe you are viewing it in a slanting way, so you will not get an accurate reading that way. So with all of that I've been talking about in this class, we come to the end of this first topic, which I call introductory topic in physics. So we're going to be building on this with motion in the next class. So till we meet again, keep learning, keep reading, keep working, and physics is easier when you give it all it takes to be consistent in reading it, in studying it, so you get better in it. So till we meet next time, do have a nice time. Bye.